It's time for Maths with Mr. Thomas.
Hi, folks. Chapter 3, lesson number 16. This is a review lesson for integration. Woo! We have made it to the end of this chapter. Well done. This is the review lesson. It does not include anything new. It is just a quick recap of all the key points from this lesson. It doesn't include every slide and every example, so if there is anything you're unsure of, you're best to look back at the individual lessons, where I will go over the examples in a lot more detail. You may just wish to use this video before the exam if you want to look back and check there is nothing you have forgotten in this chapter. But as I said, if you have, look back at the specific lessons. So we started this chapter off looking at standard integrals way back many years ago. And what are standard integrals? Well, this was really what we learned in higher. We learned that if you integrate x to the power of n, you add 1 to the power and you divide by that new power. If you integrate ax plus b to the power of n, you do the same thing. You add 1 to the power and you divide by the new power. Except what you need to remember is that you have to divide by the derivative if you have x with something in brackets to the power of some value. So you would divide by the derivative, you would divide by a, hence where that a comes from. So if you have something like this, well, you know the first thing you would do is write any root signs as to the power of a half. You'd split this up, so you're dividing each part by x to the half. Rewrite that then, so 3x squared over x to the half, subtract the indices, so it's 3x to the power of 3, deal with the other bit as well, move that to the top, make the index negative, and from there it's just some basic examples with integration. Add 1 to the power, divide by the new power. If you add 1 to the power, you get 5 over 2, but remember when you divide by 5 over 2, when you divide by a fraction, that's the same as flipping it upside down and multiplying by that. So that's the same as multiplying by 2/5. And the 3 would stay as it is. So that was the first example, just looking at standard integrals. We then looked at more. We looked at if you have limits and for integrating the square root of 4x plus 1, well, we'd write that as 4x plus 1 to the half. Add 1 to the power, divide by the new power, but remember to divide by the derivative of what is in the brackets. Don't forget to do that. And you're integrating between 2 and 0. So you'd sub in 2, you'd sub in 0, obviously working that out, 2 times 4 is 8, add 1 is 9, that's where the 9 comes from. Work that out and then you will get down to your answer. But most importantly, as I said, just remember to divide by the derivative of the brackets. After that, after we looked at standard integrals from higher, we moved on to looking at e to the power of x. Integrating e to the power of x is dead easy. Do you remember what do you get? Good, you get e to the power of x. If you integrate e to the power of anything else, so if you have ax plus b, it stays as it is, but you divide by the derivative of the index. So, for example, here, if you integrate 6e to the power of 3x, the 6 will stay, e to the 3x will stay, but you divide by the derivative of the 3x. Differentiate 3x, you get 3, so we're dividing by the 3. The same with this one as well. The 4 stays, e to the negative x stays, and you would divide by the derivative, which will be negative 1. And then you can simplify all that. So integrating e to the power of x, probably the easiest part of the advanced higher course. It just stays as it is. Just remember to divide by the derivative. You can apply that to harder examples. With this one here, you had to multiply out the brackets first of all. Then, similar to that very first example, you had to divide by e to the power of x, rewrite it all, and then you were integrating. After you integrate, you were subbing in the 1 and the 0. Then, we moved on to look at natural logs, ln. So if you have 1 over something, well, you know you've differentiated ln x. So differentiate ln x, you get 1 over x, but that is only true for when x is bigger than 0. You can see here, if you extended that and your graph went into the negatives, the graph does not exist. Hello, where are you? It's not there. So ln x is only defined when x is bigger than 0. This means if you go back the way and you have 1 over x and you integrate, you will get ln x, but only when x is bigger than 0. So what do you do when x is less than 0? Well, that's when we bring in what's known as the modulus, or the exact value of a number. And that is denoted by writing the number with these modulus signs. And it's the non-negative value of x, regardless of whether x itself is positive or negative. So the absolute value of 2 is 2. The absolute value of negative 3 is, forget the negative, is just 3. Which means then that if you integrate 1 over x Because it's only true when x is bigger than 0, you would put in these modulus signs to show us the absolute value. So it's always non-negative. And that will be true for all non-zero values of x. So if you integrate 1 over x, you get ln x. If you integrate 1 over ax plus b, you get ln ax plus b. But once again, you have to divide by the derivative of what the x part is with. So you've got ax plus b, so you divide by a. Note, 2 notes, the modulus signs are not necessary if we know x is a positive, and also that rule only applies to linear functions. So it wouldn't apply to the likes of this because you've got your quadratic on the bottom. Integrating then, if you integrated x over 2x plus 1, you can imagine that is 8 times 1 over 2x plus 1. So the 8 will stay. 1 over 2x plus 1 goes to ln 2x plus 1 with the modulus signs. But remember, you have to divide by the derivative of that part. So you divide by 2. And then you can simplify it and get your answer. Obviously, put in your plus c. We tried some harder examples with this one here. We were just integrating once more, but we had limits between 14 and 2. So 1 over 2x take away 1. If you integrate it, we got ln 2x take away 1. Divide by the derivative. So divide by 2. And we had that between 14 and 2. Just remember from that first note, you don't need the modulus signs if you know x is positive. And here we are putting in positive values. And if we double it, take away 1, we're still getting positive values. So we definitely don't need the modulus signs here. You end up with 27 and 3. From there, we just simplified that. Again, if you are wanting this in more detail, look back at these individual lessons. This is just a quick recap, or quickish recap, of all the key points. Trig functions. We know that if we integrate and if we differentiate, then we can do that with sine and cos. We can integrate sec squared as well, and that gives us tan. And we can take this a step further to get integrating sine of ax plus b is just negative cos ax plus b. But you have to divide by the derivative of what's in the brackets. The same with cos ax plus b goes to sine ax plus b, but divide by the derivative. And the same with the sec squared. We tried some examples then. If we had 6 sec squared 4x, well, the 6 will stay as it is. Sec squared, if we integrate it, goes to tan, so it'll go to tan of 4x, but divide by the derivative of the part that's in the brackets. And here you're imagining in your head that that is sec squared of 4x, so you're dividing by 4. And that is where that quarter comes in. After that, simplify that, and you get 3 over 2 tan 4x. The next thing we did was we spent 6 years looking at integration by substitution. And the first thing we noticed was that we can use it if we have a product, if we are multiplying one function by another function. Because if we don't, we'd have to multiply out the brackets, and that would take us a very long time. So we can use integration by substitution by being given a substitute. So here we're told u equals x squared plus 1, and we want to integrate using that substitution. So to do that, what we do is we think, right, well, if u is x squared plus 1, then we know this bit in the brackets is going to be u. So we will have u to the power of 5. However, we also have a dx and we've got an x. What we need to do is we need to go from this line to writing it all in terms of u. And to do that, we take our substitute and we differentiate it with respect to x. So differentiating u with respect to x will be du by dx, and on the right hand side we'd get 2x. Multiply both sides by dx and then divide by 2, and that way we have found what x dx is equal to. And look up here, it was x dx that we wanted to find, so we know x dx is a half du. So x squared plus 1 to the power of 5 becomes u to the power of 5, and then there's a dx and x becomes a half du. And then from there you can rewrite it, put the fraction first, u to the 5 du, integrate with respect to u, and then finally you would rewrite that in terms of x. There were loads of examples with that. And then we went on to look and applied it to quotients as well when we're dividing one function by another function. It's the same idea. We've still got our substitute. We're told u equals 3x squared plus 1 in this example, so we know the bottom line there will go to u. So we'll have x over u dx, but we can't have x's and u's in the same question, so we need to find what x dx is equal to. Go down the same path, differentiate u, so du by dx, multiply both sides by dx. Then think, I want an x dx, I've got a 6x dx, so divide both sides by 6. And then you've found out what x dx is equal to. After that, we know what x dx is, so we can sub that in, or the 6th du in place of that. So we will have 1/6 du, and then the 1 over 3x squared plus 1 becomes 1 over u. And that's what you would get. Look back to the example if you're not sure. After that, we looked at manipulation. Why do we need to learn about manipulation? Well, because a lot of the time what you'll find is that when you're using your substitution, the likes of this question here, we're told u is the x plus 1, so we know then we can replace that with u. So we'd have an x times u to the power of 3 dx. So we now need to find x and dx. If we differentiate u, then what we get down to is du equals dx. So okay, we've found dx, we can write that in terms of u, we know that's du, but we also need to find out what x is, so we manipulate this substitute. So we write down u equals x plus 1, and we need to write it down in terms of x equals. We need to find out what x is. So by subtracting 1 from both sides, we can find out what x is. Once we know what x is, we can replace x with the u take away 1. We've done that. We can replace x plus 1 cubed with u cubed. We've done that. And we can replace dx with du. And then from there, multiply the brackets and integrate as normal. Just remember that you should replace your u back with whatever it is equal to. So your final answer is in terms of x. After that, we looked at definite integrals. So that is when we had limits. And when we're working with limits, what we need to remember is to write our integral down with the limits expressed in terms of the new variable. So to do that, we were again writing down, this would be u, because u is x to the power of 4 plus 1, so that's u to the power of 3. Differentiate it, do the same as we have done in the other examples. But what we need to remember is, if the limits here are 0 and 1, they're in terms of x. So write them in terms of u. And you do that by looking here, and you think u equals x to the power of 4 plus 1. So replace x with 0 to find out what u would be. That would give you a 1, so we know at the bottom we're going to have 1. And when x is 1, well, 1 to the power of 4 plus 1 is 2. So we know the limit at the top will be 2. We're rewriting all this in terms of u, and then we're just back to what we were doing. Integrate, simplify, sub in the values, and work it out. Again, look back to this individual lesson. I'll go over each part in more detail. Lesson number 9 was integration by substitution 5. This was just one example thrown into this lesson, and it was letting you know that if the integrand, the bit to be integrated, contains a term in the form the square root of a squared minus x squared, the substitution x equals a sine theta is often used. And that is because here, if you do that, well then you will get, well, x equals 2 sine theta. So the first thing we're doing is we're thinking, right, well, if x equals 2 sine theta, replace x with 2 sine theta. So here you'd have 4 minus 2 sine theta all squared, and that will give us 4 cos squared theta. That's what we'd have under the square root, and if you square root that, you'll get 2 cos theta. That will be in terms of theta, but we need dx and x plus 1 in terms of theta. So dx, if you differentiate x with respect to theta, then you will end up with what dx is equal to. So we can replace dx with what it would be in terms of theta. The limits as well, you need to express them in terms of the new variable. So doing that, well, you're thinking here it's in terms of x, so these limits are in terms of x. Replace x then in here to find out what theta would be. So when x is 0, theta works out to also be 0, so the new limit will be 0. And when x was 1, sub that in here and change so it's theta equals, and theta is pi over 6. To get this x plus 1, you're thinking, well, x is 2 sine theta, so x plus 1 will just be 2 sine theta plus 1. Sub all those parts in then, and you will rewrite it in terms of theta. Look back to the lesson if you want more detail. From there, the 2 cos thetas will cancel, giving you something you can easily integrate, and then integrate it, and you're subbing in pi over 6 and 0. Sub in pi over 6 and 0, multiply it out, and get your answer. Finally, the lesson on integration by substitution. It was looking at when there is no substitute given. So sometimes you have to decide on the substitute yourself. But always remember, integration by substitution is usually used when the derivative of one part is linked to another part. So notice here, if you differentiate x squared, you get 2x. And the x appears in the other part. So here, you want u to be equal to this part under the square root, the x squared plus 1. Doing that will give you the square root of u here. So u equals x squared plus 1, so we've got the square root of u, and we do the same thing, differentiate u with respect to x. Doing that, du by dx will equal 2x, multiply both sides by dx, so you'd have du equals 2x dx. We're wanting to replace x dx, so half both sides, and we find what x dx is equal to. Sub that in here, and then from there, you're just integrating the way you normally would, and simplifying, and then rewrite it in terms of x. After integration by substitution, we looked at inverse trig functions, and this is when we have to think back to this lesson 2.8 when we were differentiating inverse trig functions. If we have sine to the minus 1 of x, we differentiate that and we get 1 over the square root of 1 minus x squared. Differentiate tan to the minus 1 of x, we get 1 over 1 plus x squared, which means if we go back the way, whoop, then if we integrate 1 over 1 plus x squared, we'll get tan to the minus 1. If we integrate this, we'll get sine to the minus 1. We can extend that as well. This is given on the formula sheet. If we extend it, then it means 1 over the square root of a squared minus x squared is sine to the minus 1 of x over a plus c. And 1 over a squared plus x squared, if you integrate that, it's 1 over a times tan to the minus 1 of x over a plus c. As I said, that is given on the formula sheet. You need to know how to use it. So if we're integrating 1 over the square root of 9 minus x squared, well, first thing we need to do is write it in that form. So we know it's the square root, so we're using this one here. We need some number squared minus x squared. So the number squared to get 9 is 3. So we're rewriting that as a square root of 3 squared minus x squared. After that, it's just sine to the minus 1, and you would have x over 3. We went on to look at some of the harder examples. This one here, example 6, well, instead of an x squared, we ended up with 4x squared. So what we need to do is we need to think what in terms of x do we square to get 4x squared? And the answer was 2x. If we square the 2x, well, that will give us the 4x squared. So here, while we're looking at this one, we're looking at tan to the minus 1. And we're thinking 9 is 3 squared. So when we're working through this, we've got 1 over a, so it'll be 1 over 3. We've also got this tan to the minus 1, and x over a, well, the x term that we're squaring is 2x. So we'll have 2x over 3. But what we need to remember is that x has been replaced with 2x. So when you integrate, you divide by the derivative. So we divide by 2, which is where this half comes in, and then simplify that. There are plenty more examples with that in the lesson. We also looked at using integration by substitution and applying that to these questions. Look back to this lesson if you are wanting this in more detail. This is just a quick recap of something you need to be able to do. If you want the whole explanation, look back to the lesson. But really, u equals 2 sine x, so you go down the route of differentiating with respect to x. Also, that 1 plus 4 sine squared x has to be written in terms of u, and you need to identify that 4 sine squared is just this squared. It's 2 sine x squared. So if you square that, the bottom line then will become 1 plus u squared. And remember, you've got limits, and what do? You need to write the limits in terms of the new variable, so the limits must be written in terms of u. This is them in terms of x. So when x equals 0, sub that in here to work out u. When x equals pi over 6, sub that in to work out u, and that gives you the new limits. Rewrite this all in terms of u, and you get 1 over 1 plus u squared with the new limits coming in at this stage, times by the half du. Integrate that using the inverse trig functions, and then after that, you're just simplifying it and getting down to your answer. After that, after integration by substitution and inverse trig functions, we went on to look at integration using partial fractions. Partial fractions popped up in chapter 1, and it's often useful to use these and rewrite your rational function in terms of partial fractions before integrating, because you can then apply the integral of Well, when you use your log rules and use natural logs if you have 1 over ax plus b. So this here we were writing in partial fractions. Look back to partial fractions if you're unsure, but first you need your distinct linear factors by factorising the bottom. If you have distinct linear factors, it'll be a over the first, b over the second, and then you can add your fractions, cancel out the denominators, and then you get down to the numerators being equal. You can find different values by find the a and b by setting x to be different values. So if x was -2, you find b. If x was a half, you find a. And you've rewritten that in its partial fractions. What you then do is you think, ooh, well, if I'm integrating that, I'm rewriting it as partial fractions before I integrate. So the 3 will stay, ln 2x take away 1 will stay, but you have to divide by the derivative of what's in the bracket, so also divide by the 2. Here you're taking away 1 over x plus 2 goes to ln x plus 2. And remember, modulus signs when you're integrating 1 over x or 1 over ax plus b. After that, we then looked at what you do when you have an improper rational function. And remember, Dracula. Rawr. You have to think Dracula must suck blood because you're going to be using algebraic long division. D for Dracula, D for divide, M for must, M for multiply, S for suck, S for subtract, B for blood, B for begin again. So you have to divide first of all. Just remember x squared add 4x plus 2. You're dividing that by x plus 1. Divide the first term, so x squared divided by x is x. Then multiply x times 1. Subtract. So subtract them and you get 3x plus 2. And then begin again because the degree of 3x plus 2 is equal to the divisor with x plus 1. The degree is 1, so keep going. Divide the first terms, 3x divided by x is 3, 3 times x is 3x, 3 times 1 is 3, and then subtract, you get -1. Degree here is less, so you stop. When you write this as a polynomial and the proper rational function, well, the polynomial is your answer, and the answer is written at the top, so that's x plus 3. Because you've got -1, you can say it's take away 1 over, and the divisor remains the same. You're rewriting it in that form because it makes it dead easy to integrate that. If you integrate x, simple. Integrate 3, simple. Integrate -1 over x plus 1, well, negative stays, and 1 over x plus 1, simple. You're just applying this rule here. After that, the final thing with integration was integration by parts. And you know when differentiating two functions, you would use the product rule. When integrating, you can use integration by substitution, or what you may wish to use is integration by parts, and sometimes you'll be asked to do that. You would use integration by parts when one function is easy to differentiate and the other is easy to integrate. So find one that's easy to differentiate and do that. Start with u and you'll get u dash. Find one that's easy to integrate, so start with v dash and integrate that to get v, and then you will use this formula here. So with this example, x times cos 2x, x is dead easy to differentiate, gives you 1. Cos 2x is easy to integrate, so that will give you a half sine x. After that, you will apply this formula, so it's u times v minus the integral of u dash times v. And doing that, if you then integrate, the first part will stay as it is. You're taking away a half and then integrate sine 2x. Integrate sine 2x is negative a half cos 2x. Two negatives make a positive, half of a half is a quarter, and the rest will stay as it is. There were loads of examples with integration by parts, but a few to point out. This one here, if you have x cubed times ln x, well, ln x has to be differentiated because the integral of ln x is unknown. So u has to be ln x, so you get 1 over x, and v dash has to be x cubed. From there, you're again just using this formula for your integration by parts. Another one to point out is integration by parts is used when you've got a product. Here it's not a product, so you have to rewrite this. Either think of it as x times 1 over the square root of x plus 4. So v dash will be 1 over the square root of x squared plus 4. Or you could write that as x plus 4 to the half, bring it up to the top line, so it's x plus 4 to the negative a half. So you've got x times that. Either way, one that you would differentiate would be x, dead easy, and then you're integrating this x add 4 to the negative a half. Obviously, if you think of it as 1 over square root of x add 4, you think about it in that form before you integrate. From there, again, you're just using this formula. We then looked at some of the harder examples, and again, a couple to point out. Here, integration by parts is used when you have a product. We don't have a product. So, how do we bring in a product? Good, it just means sine to the minus 1 of x times 1. So now we've got our products. It's 1 times something. We're multiplying two parts together. We need to find one that's easy to differentiate, one that's easy to integrate, but the integral of sine to the minus 1 of x is unknown. So we need to differentiate that. So differentiate sine to the minus 1 of x and integrate the 1. Doing that, and this is what you would get. And what you'll notice is that even though we're using integration by parts, further on we'll find we have to use another method. We have to use integration by substitution to integrate this part here. So you would then go off and think, right, well, I'm using integration by substitution, so I'm choosing the integral substitution myself. So u is 1 minus x squared, and work your way through that. Again, if you want me to explain this, look back to the lesson. This is just me saying, look, you need to know this. Do you know it? After that, we looked at integration by parts, and this time we had x squared cos 3x. Again, another example I just wanted to point out in this review, just to make sure you know how to do it. What you'll notice is that if you find u is x squared, and differentiating that gives you 2x. V dash, the one that you integrate, is cos 3x. What you'll notice though is that when you sub these into this formula, you will get again a product with that you have to integrate. And when you've got a product that you have to integrate, you would again use integration by parts. So this is one of the examples where you have to use integration by parts twice. So again, you would go to the side and you would integrate 2 over 3x times sine 3x. Do that. And if you work that out, then that will give you this answer here, and you can sub that into that previous line. So we can go back there and then we can sub that in. Again, if you want this explained in more detail, look back to that lesson. Example 15, well, this time we had limits, and really the main thing I wanted to point out was if there are limits, what you would do first of all is ignore the limits and just work out the integral without them. If you do that, you will get down to an answer plus c, but then from there what you would do is you would take that answer and then you would start subbing the limits in. So you would take your answer and you say, right, now I'm thinking about the limits, so I'm subbing in the 1 and the 0 in place of x. So doing that, that is what you would get. So if you ever get limits when it's integration by parts, ignore them first of all. It just makes it slightly easier for you. And the final example with integration by parts was one of these never-ending examples. If you're differentiating e to the x, you still have e to the x. If you're integrating cos x, you get sin x. Then if you integrate that, and integrate that, and integrate that, you're just in a sine cos loop. So you're caught in a loop with sin x and cos x, you're caught in a loop with e to the x. So it's really a never-ending question. So the way you do that is you would say that I, the integral, equals the integral of e to the x cos x, and then you start working your way through it. You will again get down to something that you have to use integration by parts again for. And if you use integration by parts again, what you'll notice is that you get back to this original question. And because we're back at this original question, well, we're calling that I, so we can replace that with I. So we can then say that we've got the integral minus, we worked that bit out, but that included an I. Get rid of the two negatives so it's plus, and then bring the i's over to one side. Once you know that what I is, or 2i is, you can divide that by 2, so you get the integral equals, and then you will get your answer with your plus c. That is a quick recap of integration. It, again, as I said, it doesn't include every slide and every example. It doesn't even go over and explain how they're all done. This is just me saying these are all the bits you need to know. Check that you know how to do them. You may even wish to pause the video and attempt the question yourself. If you can't do it, look back to the individual lesson and I'll explain how it is done. Best of luck. Any problems, let me know. Bye. Woof. Yo. Meow. Turn it off.